of any reaction means the change of either the concentration of the product with the change in time. So if we are measuring the rate as the change in concentration of the product, of course, the concentration of the product increases with time. At the beginning, we don't have any product, and then its concentration increases with time. So the rate equal a positive value, because if we subtract change in concentration of product means the final concentration of product minus the initial concentration of product, this will be a positive value because the final is greater than the initial. So the rate has a positive value. But if we are measuring the rate of the reaction as the change in concentration of reactant with time, the change in concentration of the reactant final minus product will give us a negative value. So negative, that's why we have to put here a minus sign, so that negative times negative means that the rate should be positive. Okay, and we say that as a mathematical expression, we say that the rate equal d, the concentration of product by dt. D means the change. When we put d, means the change in the concentration of the product with the change in time, or the change in the concentration of the reactant by the change in time. So this is the mathematical expression of measuring the rate. Now, how do we follow the rate of any reaction? If we want to follow the rate of any reaction, means that we want to follow either what happens to the concentration of the product with time, or what happens to the concentration of the reactant with time. So we have to do experimental methods. And of course, the experimental method depends on our reactants and our products, because we are going to follow one of them. Either we follow what happens to the concentration of the product, or we follow what happens to the concentration of the reactant. So as I told you, to follow these two values, either the product or the reactant, we have to look at our reaction and see which one of them we are going to be able to measure. So for example, if one of our products is in the form of a gas, this means that we can measure the volume of the gas produced, as we are going to see, of course, by examples. We are going to measure the volume of the gas produced with time. Or else, in other reactions, we can use the change in mass of a reaction mixture, as we used to see in O-level. Of course, also I'm going to show it to you now. Or if one of our reactants or one of our products has a color, then we can measure the rate of the reaction by measuring the intensity of the color of such a reaction by an instrument that is called colorimeter, and we call this method colorimetry. Or else we measure the change in the concentration of a reactant or a product using titration. If one of our reactants is an acid, or one of our products is an acid or a base, we can make titration to determine its concentration with time. Or if we have, for example, a reaction involving an acid or a base, we can also measure the change in pH with time. And if one of our reactants or products is in the form of ions, then we can follow the rate of the reaction by measuring the electrical conductivity, because we know that electrical conductivity depends on the presence of ions in our reaction mixture. Okay, so for example, if we are measuring the rate of such a reaction like calcium carbonate solid plus hydrochloric acid gives calcium chloride plus water plus carbon dioxide. We look here and we find that one of our products is a gas. This means that if we want to follow or to determine the rate of such a reaction, we can measure the volume of the carbon dioxide produced with time. And by the change in the volume of carbon dioxide with time, we will be able to measure the rate of such a reaction. If we have another reaction like this one, propanone plus iodine in presence of an acid to form the iodopropanone, CH3CO, CH2I, iodopropanone, and a hydrogen ion and an iodide ion aqueous are produced, we will find here that iodine has a color. We know that iodine in aqueous solution is brown in color. It is brown in color. So we will find that this brown color fades with time. The brown color of iodine fades with time as more and more of iodine reacts with the propanone to form the iodopropanone. We will find that the brown color fades with time. So in that case, since we have here a color which fades with time, then we can follow the rate of such a reaction by measuring the intensity of the brown color with time. So it depends upon our concentration. Now, let's see, for example, if we have a reaction like, for example, here, if we have a reaction of, for example, magnesium metal reacting with hydrochloric acid to form magnesium chloride plus hydrogen gas. So 1 over our products is hydrogen gas. It's a gas. So we said that whenever one of our products is in the form of a gas, then we can follow the rate of such a reaction and measure the rate of such a reaction by measuring the volume of hydrogen gas produced per time. For example, every half a minute or every 1 minute. So how do we do that? We get a conical flask. We place an excess amount of hydrochloric acid in this conical flask. Then we are going to prepare a system where there is a tube that will be placed in a trough filled with water. And in this trough, we are going to place a measuring cylinder. Of course, as you see, it's a graduated measuring cylinder in order to measure the volume of the gas produced. Of course, at the beginning, when we place such a measuring cylinder, in the trough of water, some of the water will rise up in the measuring cylinder. So we find out the volume of the water here. And then we are going to add the magnesium metal to the hydrochloric acid. And at once, we are going to cover the conical flask using the bung. And then the stopper, whatever we call it. And then at the same time, we are going to use the stop clock or the stopwatch to measure the time. Of course, here we have to use a stopwatch or a stop clock in order to measure the time. And we will measure the volume of the gas produced. Of course, whenever the gas is produced, then water will go down so that the gas will fill its place. So by measuring the difference in volume from the beginning and at the final stage, we get the volume of the hydrogen gas produced. And we measure this volume with time. Every half a minute or every 1 minute, we see what is the volume of hydrogen gas produced in such a reaction. Of course, if we want to use this method, the gas produced here should be insoluble in water, because some gases, for example, if we have hydrogen chloride gas, if we have chlorine gas, if we have carbon dioxide gas, even carbon dioxide is slightly soluble in water. So if we have any gas produced that is soluble in water, we will not be able to use this method to calculate the rate of such a reaction. We have to use a gas syringe instead of this part. So the tube will be connected to a gas syringe. So here, the gas produced here should be insoluble in water. If it is soluble, we cannot use this method. So as I told you, it depends upon the reaction itself. Now, if we have a gas that is soluble in water, then we have to introduce a gas syringe instead of the trough of water and the inverted measuring cylinder. We are going to use a gas syringe in order to calculate or to collect the volume of the gas produced. Of course, if the gas produced has a high density, then we can use this other technique. Like, for example, as we said, if we have a reaction of calcium carbonate reacting with hydrochloric acid to form calcium chloride plus carbon dioxide gas plus water. So here we have carbon dioxide gas produced. So either we are going to use the first method by collecting the carbon dioxide produced in either a gas syringe or, as I told you, if we collected underwater, part of the carbon dioxide will be lost, and it will be a not very accurate method to measure the volume of carbon dioxide with time. But there's another method when our gas is a little bit dense, like carbon dioxide gas, is to use this other technique by measuring the change in mass of a reaction mixture. Now, what are we going to do? We are going to get a balance, and we are going to get a conical flask at which we are going to place an excess volume of hydrochloric acid. And then we are going to put a certain amount of calcium carbonate lumps in the conical flask. And at once we are going to measure the mass of this conical flask containing the calcium carbonate and the HCl together. But in this experiment, we are going to place here what we call a cotton wool. We place here a cotton wool. And this cotton wool allows the gas produced, which is the carbon dioxide gas, it allows the carbon dioxide gas produced to escape outside the conical flask, whereas it prevents the splashing of the reaction mixture, because when calcium carbonate is added to HCl and carbon dioxide gas is produced, bubbles are formed here in the reaction mixture. And sometimes there will be splashing due to the vigorous reaction. Sometimes there will be splashing of the reaction mixture outside the conical flask. That's why, to prevent the splashing of the reaction mixture outside the flask, we place here the cotton wool so that it allows the escape of the carbon dioxide gas produced, and at the same time prevents the splashing of the liquid outside the conical flask. Okay, and as I told you, if we want to follow this type of reaction, measuring the mass, the gas produced should be a high density gas. We cannot use this method in the previous example where magnesium reacted with HCl to form magnesium chloride and hydrogen, because hydrogen gas is a low density gas. And if we have a low density gas, we will not feel the difference in mass as when we have a high density gas like carbon dioxide. This method is used only when the gas is a high density gas, because in that case we can measure the difference in mass between the beginning and every time. What happens, of course, as carbon dioxide escapes outside the conical flask, we will find that the mass of the conical flask will decrease with time. So we can follow the rate, or we can measure the rate of such a reaction by measuring the mass, the difference in mass between the conical flask at the beginning of the experiment and every 1 minute or every half minute, yani whatever we want. Okay. Now, what happens if we have, as we said, a reaction at which a color change is produced? As we said, if we have this reaction, propanone plus iodine in presence of acid medium, as we are going to study, of course, this method in more details afterwards, we get iodopropanone plus hydrogen ion plus iodide ion. We will see that at the beginning, iodine has a brown color, and this color fades with time. So either we study such a reaction by colorimetry, where we place the reaction mixture in a cell. This is called a cell or a cuvette. Sometimes we call it a cuvette. And we place this cuvette in the colorimeter, and we see what happens to the color of the iodine with time. Of course, as more and more reaction takes place, then the iodopropanone will be formed. And this means that part of the iodine is used up and to form the iodopropanone, and this means that the color of iodine will fade with time. But in this reaction, we have another method to be used. What is this other method? Since iodine is an oxidizing agent, it can be titrated with a reducing agent. But of course, what we are going to do here is that we have the reaction mixture, which is propanone. We are placing here propanone with iodine, and of course, in presence of an acid medium. So this is the beginning of the experiment. And then every now and then, for example, every half minute or every 1 minute, we are going to remove a sample out of this reaction mixture. And we call this sample, we usually call it an aliquot. Of course, you have to know this name, aliquot, because sometimes they give it to us in the exam paper. So we have to know that we remove a sample which is called an aliquot every now and then, every, for example, half minute of the reaction mixture. And then to this aliquot, we are going to quench it. What do we mean by quench? Quench means that we are going to stop the reaction. We are going to stop the reaction. Now, how do we stop such a reaction? Of course, every reaction, it depends on the reaction. But in such a reaction where propanone is reacting with iodine in presence of hydrogen ions, to quench such a reaction, to stop the aliquot or the sample that we are going to get out of the reaction mixture, either we add, for example, sodium hydrogen carbonate is added, so that the sodium hydrogen carbonate reacts with the catalyst, which is the acid catalyst. Of course, this reaction will not go through without the presence of the catalyst. So we add the sodium hydrogen carbonate in order to react with the hydrogen ion or the acid present as a catalyst, and the reaction will stop. Or else we quench it by placing the aliquot that we took, we place it on ice. When we place it on ice, then the reactants will not have the energy enough to collide together to form the reaction. So in such a reaction, we can follow the rate of such a reaction by either two ways. As I told you, the first way is to follow the color of the iodine throughout the reaction. Iodine at the beginning is brown, and then with time, this brown color fades with time. So we can place the reaction mixture in a cuvette or in a small cell, as you see here, and we place it in an instrument that is called colorimeter, which measures the intensity of color with time. And we see what happens to the intensity of color with time. This is the first method. Or the second method is that we know that iodine is an oxidizing agent. Iodine is an oxidizing agent. So we can titrate, we use titration of iodine using what we call here sodium thiosulfate, which is a reducing agent. So we make a redox titration reaction between the iodine that is present at the beginning with the reducing agent. So how are we going to do this titration in order to follow or to calculate the rate of such a reaction? At the beginning, as I told you, we are going to bring the propanone plus iodine in the presence of the acid catalyst. And after, for example, half a minute or 1 minute, we are going to remove an aliquot or a sample of the reaction mixture, leaving it to complete the reaction. We took this sample to study the rate at this time. We remove an aliquot, we quench it either by adding sodium hydrogen carbonate to react with the acid that is used as a catalyst so that the reaction is stopped in the sample, or else we take this sample and place it over ice to stop the reaction between both reactants. Then after we stop the reaction, what are we going to do? We are going to titrate the iodine present in this sample with the thiosulfate and find out the concentration of the iodine at this time. Okay, so after we quench the sample, we are going to titrate it with sodium thiosulfate, which is a reducing agent, in order to find out the concentration of iodine at that time. Of course, we took only a sample and the rest of the reaction mixture was continuing. So after another half minute or another 1 minute, we are going to take a new sample or a new aliquot of the reaction mixture and repeat these steps, quench it, and then titrate against sodium thiosulfate and find out the new concentration of iodine in the new sample. Of course, what happens to the concentration of iodine with time? Does it stay the same or does it change? Stays the same or change?
Changes.
I can't hear you, Salman.
It changes.
Yes, excellent. It will change because at the beginning it has a certain concentration, and as the reaction goes by, iodine reacts with the propanone and part of it reacts, and this means that the concentration decreases with time. And this means that also the rate will decrease with time. We know that always the rate starts high and then it decreases with time. Okay, do you have any question here?
No, miss, I don't.
Okay. Now, also, if we have such a reaction like bromide reacting with bromate in presence of acid medium to get bromine and water, so here we find that our reactants are in the form of ions, bromide, bromate, and hydrogen ions. All these are ions, and of course, the electrical conductivity of ions here will be high. And with time, they change to other substances that are not in the form of ions. And this means that the electrical conductivity will decrease with time. So we can follow the rate of such a reaction by measuring the electrical conductivity with time. With time, we will see that the electrical conductivity decreases with time as ions are going to be used to form the products. So their numbers will decrease. And when the number of ions decrease, then the electrical conductivity also decreases. So as you see that, of course, we have here another type of measurement, which is called dilatometry. And in that case, we measure the change in the volume of liquids in an instrument called dilatometer. And this means that we can use any physical property for reactions, for any reaction, in order to determine the rate of such a reaction. Depending on the type of reaction, whether it produces a gas, then we can measure the volume of the gas either by this technique or by using the gas syringe, or if there is a difference in mass produced, we can follow the rate of the reaction by this method. Or if we have a reaction at which a color is either found in the reactants or the products, we can measure the intensity of color with time, or else we use titration methods, or else we use measuring electrical conductivity or any other physical property found in the reaction mixture we have to follow in order to calculate the rate of such a reaction. So this is the experimental methods. And of course, sometimes they give you in the past papers, you will find that, of course, you have the first part is multiple choice questions. So sometimes you are going to be asked about what is the proper method to use in order to follow the rate of such a reaction. And they will give you a certain reaction and give you four, of course, answers. And you have to choose the answer that is suitable with the type of the reaction you are dealing with. Now we come to something called the rate equations, the rate constants, and orders of the reaction. Now, what is the rate equation? The rate equation is an equation that gives us the relationship between the rate of the reaction and the concentration of the reactants. The rate equation is an equation that relates the rate of the reaction with the concentration of the reactants. So here, if we have a reaction like this, A gives B, So we only have one reactant only. And we see that, for example, we see that we are going, of course, to study how to find out these rate equations. We find that the rate of the reaction is directly proportional to the concentration of this reactant A. It is directly proportional, means that as the concentration of A increases, the rate of the reaction increases. If the concentration of the reactant A doubles, the rate doubles. If the concentration of A is 3 times, we will find that the rate also becomes 3 times. So this means that there is a direct relationship between the rate of the reaction with the concentration of A. So we say that rate equals K times A. We call this the rate equation, which related what happens to the rate as the concentration of the reactant A changes. As A is doubled, the rate doubles. As A triples, rate triples, and so on. So there is a direct relationship, and the rate equation will be the rate equals K times A. And we call K, we call it the rate constant. Of course, this is the proportionality constant that relates the rate to the concentration of A. Now, if we have such a rate equation, that the rate is directly proportional to A, as if the concentration of A is raised to the power 1. So we say that this reaction is a first order reaction. We say that this reaction is a first order reaction with respect to A. First order means that there is a direct relationship between the rate and the concentration of A. We call it a first order reaction. Okay, but if we calculate the rate equation and we find that the rate equals K times A to the power 2, what does this equation means? When we say that the rate equals K times A to the power square, it means that as A doubles, as the concentration of A doubles, we find that the rate quadrupoles. What do we mean by quadrupoles? It means that the rate becomes 4 times. We measure the concentration of A and we measure the rate, and then we double the concentration of A and then we measure the rate again. If we double the concentration of A and we find that the rate does not double as well, like in this case, but instead it becomes 4 times the first rate, then this means that we can put our rate equation in this form, rate equal K times A to the power 2, which means that we have what we call a second order reaction with respect to A. I will repeat this. If we measure the rate of such a reaction, how it depends on the concentration of A. Now we get a certain concentration of A, for example, 0.1 mole per decimeter cube, and find the rate. So we say that if the concentration of A is 0.1 moles per decimeter cube, the rate was rate 1. Okay, but if we double the concentration to 0.2, we find that the rate equals 2 times the rate 1. So there is a direct relationship between the concentration of A and the rate. When the concentration was a certain value, the rate was a certain value. When we doubled the concentration of A, we find that the rate also doubles. So we say that the rate equation is rate equals K times A, and we say that this is a first order reaction. But if in another experiment, we make the concentration of 8.1 moles per decimeter cube and we find the rate is a certain value. If we double the concentration of A, we find that the rate becomes 4 times the first rate, not 2. We doubled here, we find that the rate becomes 4 times the first rate. So, and if we triple the concentration of A, we find that the rate becomes 9 times the first rate. So we say that there is a relation that the rate equation is the rate equal K times A squared. And we say that this is a second order reaction. Understand, Salman, or shall I repeat this?
Yes, I understand.
Okay. Now, in other reactions, we find that, for example, if we started with the concentration of A to be 0.1 moles per decimeter cube, we find that the rate is rate 1. If we double the concentration of A, we find that the rate does not change. It stays rate 1 as it is. If we triple the concentration of A, we find that the rate also stays the same. What does this mean? It means that the rate is independent on the concentration of A. It does not depend on the concentration of A. Whenever we change the concentration of A, we find that the rate stays the same. And in that case, we can write the rate equation as rate equal K times A to the power 0. To the power 0 means anything to the power 0 means 1. It means that the rate does not depend on the concentration of A. It is not affected by the difference in the concentration of A. Whenever we change the concentration of A, the rate remains constant. And we call this reaction, we call it a zero order rate equation. Zero order means that the rate is independent on the concentration of A, and the rate equals the rate constant itself. Okay, this is if we have only one reactant. Now, what happens if we have two reactants? A plus B gives C. So in such a reaction, for example, we are going to study the effect of changing the concentrations of both A and B on the rate of the reaction. Here, we only changed the concentration of A because we only had one reactant. But if we have two reactants, A and B, we have to study each of them and its effect on the rate of the reaction. So if we measured, of course, we are going to take how we do this because we are going to study this in more details, but now we are just studying what does rate equation mean? What does a rate equation mean? So if we have two reactants, like in this case, A plus B, and we find that the rate equation is that the rate equal K times the concentration of A squared times the concentration of B. What does this mean? It means that if the concentration of B was, for example, 0.1 and the rate was rate 1, so if we double the concentration of B to 0.2, we find that the rate also doubles. If we triple the concentration of B, the rate also triples. Then we say that the rate is directly proportional to the concentration of B, or we say that the rate equals K times the concentration of B. And it is a first order with respect to B, because as we change the concentration of B, the rate will change in the same way, exactly the same way. But if we do other experiments and we find that if we started by the concentration of A to be 0.1 and the rate was rate 1, and if we change the concentration to 0.2, we find that the rate becomes 4 times the first one. If we change the concentration to be 0.3, we find that the rate becomes 9 times rate 1. So this means that the rate is directly proportional to A squared, not just A. And this means that the rate equal the rate constant times the concentration of A squared. So if we combine these two equations, we get the overall rate equation, which is that the rate equals K, rate constant, times the concentration of A squared times the concentration of B. And we say that this is a third order reaction. Third order reaction. It is first order with respect to B and second order with respect to A. So we add both orders, 2 plus 1 makes 3. So we say that it is a third order overall. We call these rate equations that relates the rate of a reaction with the concentration of one of the reactants. Of course, we do this experimentally. We cannot find the rate equation just by looking at the stoichiometry of the equation. We don't say since we have A and B, then the rate is directly proportional to A and directly proportional to B. We can't say so. We have to do experimental methods in order to determine the rate depending on the concentration of B and the rate depending on the concentration of A, and then at the end formulate our rate equation and find out the order of such a reaction. Of course, we are going to see how do we make these experiments and how do we get this rate equation. But here at the beginning, we want to know what is a rate equation. Do you have any question?
No.
Okay. So if we want to look at the units of the rate constants, we know that we said that the rate is the change in concentration by the change in time. And this means that the units of any rate is mole per decimeter cube, second minus 1. The units of the concentration is mole per decimeter cube, and the time is in seconds, so we get it up here as second minus 1. This is the units of rate, and the unit of the rate is constant. Always when they ask about the unit of any rate, it is mole per decimeter cube per second. But if we want to know the units of the rate constant, of course, it depends on the rate equation. If our rate equation is that the rate equal the rate constant times the concentration of one of the reactants, this means that the rate constant equals the rate divided by the concentration of A. The unit of the rate is always constant. It is mole per decimeter cube, second minus 1, divided by the concentration of A, which is mole per decimeter cube. So mole per decimeter cube cancels with mole per decimeter cube, and the unit of such a reaction is the rate constant is second minus 1. This is if it is a first order reaction. Now, what happens if it is a second order reaction? We say that the rate equals K times A squared, or K times A times B. In both cases, we have a second order reaction. So the rate constant K equals rate divided by the concentration of A squared equals, the units will be mole per decimeter cube per second divided by the concentration of A squared, which is mole per decimeter cube squared. So mole per decimeter cube goes with one of these squares, and we get, if we transfer the mole per decimeter cube upward in the numerator, it will be mole minus 1 decimeter cube, and then we put the second minus 1 that was present at the beginning, and this will be the unit of the rate constant if we have a second order reaction as such. Now, what happens if we have a zero order reaction? Zero order reaction, we said that a zero order reaction means that the rate does not depend on the concentration of A. The rate equals K times A to the power 0. This is a zero order reaction. And we said that anything to the power 0 is equal to 1. This means that the rate equals K. And in that case, the units of K is the same as the units of the rate, which is mole per decimeter cube per second. This will be the unit of the rate constant, which is K. If we have a third order reaction, we will find that the units of the K, which is the rate constant, is decimeter to the power 6, mole to the power -2, second -1. So as you see here, the units of the rate constant depends on our rate equation. We don't have a constant value for the units or a constant unit for the rate constant. It depends whether we have a zero order reaction or a first or a second or a third order reaction. It depends on our rate equation. So if we want to write our rate equation in general, we say that if we have, for example, 3 reactants, A, B, and C, then the rate equation, the rate equals the rate constant K times the concentration of A raised to the power M times the concentration of B raised to the power N times the concentration of C raised to the power P. Of course, M, N, and P could be 0, could be 1, could be 2, whatever. And the overall order means that we are going to add all these powers together. For example, if we have M to the power 1 is equal to 1, N is equal to 1, and P is equal to 2, then the overall order will be 1 plus 1 plus 2 makes fourth order reaction. Of course, we are not going to deal with a 4 order reaction. Maximum, we have third order reaction in our studies. But this is how we get the rate equation. And as I told you before, that we don't get the rate equation by just looking to our reaction, by the equation of the reaction. We cannot determine the rate equation by such. We have to do experimental methods in order to get the rate equation. Okay. Now we come to something called the reaction mechanisms. What is a reaction mechanism? The reaction mechanism is the steps by which a reaction takes place. Because not all reactions, we find that, for example, A plus B gives C. When we studied before in O-level and in AS, we took what we call the collision theory. And the collision theory stated that for such a reaction to take place, A and B should collide together with proper orientation and with energies enough, which is equal to or greater than what we called the activation energy, in order to form the product C. We studied this before. We studied about the collision theory, and the collision theory stated that for such a reaction to take place, then A and B should collide together with proper orientation. They must be oriented in a proper situation with respect to each other, and must have energies enough to form the product. And this energy, we call it the activation energy. So the collision theory stated that the reactants should collide together. Now, if we look to such a reaction, manganate ion plus 8 protons plus 5 iron plus 2 to give Mn plus 2 plus 4 water plus 5 Fe plus 3, we find that we have 3 types of reactants, but manganate 1 mole should collide with 8 moles of acid and collide with 5 moles of iron plus 2 in order to form this reaction. Of course, this is an impossible situation. Impossible that we have here 14 substances or 14 species colliding together in the same moment in order to form the reaction. This couldn't happen. And this means that this reaction to take place and form the product, it should take place in more than one step. That every 2 species collide together, or maximum every 3 would collide together in a step, and then in another step the product will collide with the rest, and in a third, the product will collide with others until we reach the end of the reaction. They cannot collide together in only one single step. That's why we call our reactions having reaction mechanisms. Mechanism means that such a reaction doesn't happen in one step. It happens in more than one step. And during these steps, every product will be formed in a different step than the other. But the overall equation will give us these whole products. Now, in the reaction mechanisms, we have to differentiate between two steps, or two different types of steps. We have slow steps and we have fast steps. Usually, the slow step is only one step. The slow step is usually only one step, and we call it the rate determining step. We call it the rate determining step. And then we have fast steps, other fast steps. Now, what do we mean by the slow step or the rate determining step? From its name, rate determining step, it shows us that this slow step is the step that is responsible for the rate of the whole reaction. In the reaction mechanisms, where reactions takes place by more than one step, we have to differentiate between two different types of steps. We have a step that usually it's only one step, that we call it the slow step or the rate determining step, and the other steps will be fast steps. The slow step, we call it the rate determining step. And from its name, it's obvious that the slow step is the step that will determine the rate of the reaction as a whole, whether the reaction will take place fast or will it take place in a slow pattern or intermediate. It determines the rate of the whole reaction as a whole. To understand this, they gave us an example here of these three students that are responsible of collecting about 10 sheets of papers together and stapling them so that they will give them to other students. So we find that we have three students. The first student is responsible of collecting these 10 sheets together. She's going to take a paper from the first pile, another paper from the second, a third, a fourth, a fifth, and so on, and collect these 10 papers together, then handle them to the next student, who's going only to arrange the papers so that they become neat, and then give it to the third student that is going to staple the papers together. As we see here in these three steps, the first student will take the longer time because she is responsible to collect 10 papers from these 10 piles. So of course, this will take time, but these two students will not take time. The second student is just arranging the papers together and giving it to the third student, who's going only to staple the papers. Of course, they will not take any time, but the first student will take time to collect these 10 sheets. So it depends on her work, that will she take, for example, 1 minute to collect the papers or 2 minutes. So the rate of these three students together depends on her. This is the slow step. The first step here is the slow step because it takes more time to happen. But these two other steps are fast steps. They will not take any time to tidy the papers or to staple them. They will not take time. But the whole method depends on the first student, which is the slow step or the rate determining step. This is what happens in any reaction that takes place in more than one step. We have a slow step and we have fast steps. But the slow step should not always be the first one. It depends on the reaction. It could be the first step, or could be the second, or could be the third. It depends on our reaction. But here, from this process, we found out that there should be a slow step in a reaction and other fast steps. And the slow step, we call it the rate determining step. Okay, do you have any question here?
No, miss, I don't have.
Okay, thank you. Now, we said that to determine the order of a reaction, we said that, for example, we say that the rate is first order with respect to one of the reactants, or the rate is second order with respect to this reactant. How can we determine the orders of these reactions? We said that the orders are determined experimentally. We cannot just look at the reaction equation and determine the rate equation. We can't do so. We have to determine the order, either 1 or 0 or 2 of each reactant by making certain experiments. Now, what are the different types of methods from which we can determine the rate equation and determine the order of the reaction with respect to one of the reactants? Now, we have two methods that we can do experimentally to determine the rate equations and find out the order of the rate with respect to one of the reactants. The first method is called the continuous method, and the second method is called the initial rate method. Now, what is the continuous method? In the continuous method, we are going to prepare our reaction mixture, as we said before. We are going to prepare our reaction mixture. And we are going to withdraw or take out samples or aliquots of this reaction mixture, and we are going to quench the sample or aliquot and find out the concentration of one of the reactants that we want to determine. So in this method, which we call the continuous method, we are going to prepare our reaction mixture and withdraw every, for example, 1 minute. We are going to withdraw a sample or an aliquot of this reaction mixture, quench it, either by adding something that will stop the reaction of one of the reactants, or by putting it over ice, and then make titration or any other method that we used before, and determine the concentration of the reactant that we are studying every, for example, 1 minute or every half minute, it means with time. And then we are going to find out the concentration and time. For example, when the time was 0 at the beginning of the reaction, we used a concentration C1 of this reactant. Then after time 1 minute, what happened to the concentration? Of course, as it is a reactant, the concentration will decrease. After 2 minutes, what happens to the concentration, and so on. And then we are going to draw a graph between the concentration of the reactant with time. We are going to draw a curve or a plot between the concentration of the reactant with time. Of course, the concentration of the reactant decreases with time. But will it always give us this straight line? No. We are going to see what do we get. And from the shape of the curve, we can determine whether we have a 0 order, a first order, or a second order reaction.